Hello student, I will be delivering a lecture on the topic infrared spectroscopy part 2nd, and this part mainly focus on application of infrared spectroscopy. As you know, the infrared spectroscopy can be used to distinguish one compound from another. No two molecules of different structure will have exactly the same natural frequency of vibration. Each will have a unique infrared absorption spectrum. Second one is obtaining structural information about a molecule. Absorption of IR energy by organic compound will occur in a manner characteristic of the types of the bond and atoms in the functional group present in the compound. And finally, the known structural information is summarized in the correlation chart. The application of IR can be summarized as it is most useful in providing information about the presence or absence of specific functional groups. It can provide a molecular fingerprint that can be used when comparing samples. If two pure samples display the same IR spectrum, it can be argued that they are the same compound. And it does not provide detailed information or proof of molecular formula or structure. It provides information on the molecular fragments, specifically functional groups. Therefore, it is very limited in scope and must be used in conjunction with other techniques to provide a more complete picture of the molecular structure. Here the representation of a typical IR spectrum. Here, although the entire IR spectrum can be used as a fingerprint for the purpose of comparing molecules, the 600 to 1500 per centimeter range is called the fingerprint region, and this is normally a complex area showing many bands frequently overlapping each other. The pattern of absorption in this region are unique to any particular compound, just as a person's fingerprint are unique. Here you see the spectrum has two parts. One is fingerprint region and second one is a diagnostic region. And when we interpret the IR spectrum, first the IR spectrum, infrared spectrum of a compound, represent its energy absorption pattern in the infrared region and is obtained by plotting percent absorbance or transmittance of infrared radiation as a function of wavelength or wave number over a particular range. The strategy for spectrum interpretation: first look at the high wave number end of the spectrum, that is more than 1500 per centimeter. That is called diagnostic region, and concentrate initially on the major bands. For each band, shortlist the possibility by using a correlation chart and use fingerprint region for the confirmation. Next, do not expect to be able to assign every band in the spectrum. Keep cross-checking wherever possible. Band intensity should be treated with some caution. Publish description of band intensities. Under certain circumstances, they may vary considerably for the same groups. Study any variation between spectra obtained by different sampling techniques. Here is the representation of IR, again IR spectrum. You see in fingerprint region, the skeletal vibrations are observed. Mainly bending, rocking or somewhat stretching vibrations are recorded here. But this region is very complicated. Mainly CO, CN and CC single bond vibrations are recorded here. But more than 15,000 to 400 per centimeter, this region that is called diagnostic region, where so many bonds are absorbed, and these are some double bonds triple bonds and some other bonds also. Double bonds, they are absorb around 1500 to 2000, that is C double bond O, C double bond C and C double bond N. And between 2000 to 2500 there is C triple bond C and C triple bond N. Here triple bonds are observed here, and here more than 2500 to 4000. Here so many stretching vibrations are recorded, and CH stretch, either it is sp3 hybridized, sp2 hybridized and sp hybridized, they are recorded here. And in this region also OH and NH stretch also recorded. In second spectrum, which is shown in here is first, if we start from 1500 per centimeter, the first sharp needle signal that correspond to C double bond C bond, C double bond C bond, you call it double bond, and that is around 1500. At around 1700 per centimeter, we can see a little bit thicker finger-like C double bond O bond, and a little bit further around 1700 to 2000 per centimeter, we might have the aromatic overtone that look like fangs, a long sharp tooth of dog, and their size is not clearly defined, and we depict their overtone here. And then we can see a very sharp needle-like signal at around 2100 to 2300 per centimeter that could correspond to C triple bond C and C triple bond N. Now here we signal at around 2700 to 2800, that is really hard to interpret, and this is an aldehyde. Sometimes this signal occur, but actually we don't have an aldehyde. So causes a little before 3000 per centimeter, we expect sp3 hybridized carbon, that is alkane, atom attached to hydrogen. Sometimes they are smaller or larger than other signals. And a little bit after 3000 per centimeter, we expect sp2 hybridized carbon alkene atom attached to hydrogen, and after sp3 and sp2 comes the sp hybridized carbon, that is alkyne atom bonded to hydrogen, and then further past 3000 per centimeter to 3700 we encounter with the large signal of a OH group, and the OH stretch show up in this region is a large singlet because it is more acidic, and in the same region as the OH we might have an NH stretch, and the NH may show a singlet, a doublet or even a triplet sometime, which depend on whether we have a primary or secondary amine, and these signal are more shorter than OH signal. And in the region where the triple bond exists, we can have a shorter version of that, which is the NH bend. This occur for primary amine and amides, and for the end carboxylic acids, this signal appear from OH stretch to between an aldehyde and a triple bond, and this signal is very wide and short. Here some stretching vibrations and their frequencies, and the alkanes generally observed at 2800 to 3000, alkene again 3000 to 3100, alkyne after that 3000 300, and OH in alcohol or phenol, it is observed at 3600 to 3650 if OH is free, and if either by H bonded, the signal is broad and it is recorded at 3600 to 3650, but in case carboxylic acid, the OH recorded at 2500 to 3300. In case of amine, the NH stretch again recorded at 3300 to 3500, and again aldehyde, it is recorded as 2720 to 2820. Again alkene C double bond C recorded at 1600 to 1680. C double bond C in aromatics or alkenes you call it. In aromatics, it recorded at 1500 to 1600, and C triple bond C alkynes, it recorded at 2100 to 2270. But in case of aldehyde, ketone, carboxylic acid, and this CO recorded at 1680 to 1740, and C triple bond N in case of nitriles, it recorded in the region of 2220 to 2260. Here is the again a larger view of some absorbed vibrations and either stretching, bending, etc. In case of alkane, the again this CH stretching again recorded around 3000, and again CH bending again recorded in the region of again 800 to 1200. In case of alkene, the CH stretch again recorded after 3000 per centimeter, but in case of C double bond C stretch, it recorded again nearly it is recorded at 1600, you call it 1500 per centimeter to 1650 per centimeter, and CH bend, it is recorded around 800 to say 1100 per centimeter, and all these compounds having stretching and bending values are showing here. You can see and observe the values. Now we discuss about alkanes. The spectra of simple alkanes are characterized by absorption due to CH stretching and bending. The CC stretching and bending bands are either too weak or too low a frequency to be detected in IR spectroscopy. So CC stretching are absent. I think in simple alkanes which have very few bands, each band in the spectrum can be assigned CH stretch from 3000 to 2850 per centimeter. Again, this is before 3000, and CH bend or scissoring from 1470 to 1450 per centimeter, and these these are the CH rock and CH rock, and that recorded at fingerprint region, that is 1370 to 1350. These are basically CH bending vibrations, and CH rock methyl seen only a long chain alkanes from 725 to 720, and these CH bending and CH stretching are clearly shown in the figure. Again, the example of alkenes, beside the presence of CH bond, alkenes also show sharp medium band correspond to the C double bond C bond stretching vibration, at about 1600 to 1700 per centimeter. Some alkenes might also show a band for the double bond CH bond stretch appearing around 3080 per centimeter. That is just after 3000 as shown here in spectrum. However, this band could be observed by the broader band appearing around 3000 per centimeter, and CH bending vibration from 1000 to 650 centimeter. And here you saw CH bending here and C double bond C stretch and in the spectrum, and CH alkane CH stretch and alkene C double bond CH stretch before 3000. Here is the sp3 hybridized CH stretch, and after 3000 it is CH alkene sp2 hybridized CH stretch. And again, this is the case of alkyne. The most prominent band in alkyne correspond to the C triple bond C. It shows a sharp weak band at about 2100 per centimeter. The reason it's weak is because the triple bond is not very polar. In some cases, such as in highly symmetrical alkynes, it may not show at all due to the low polarity of the triple bond associated with those alkynes. As you see in the spectrum, a terminal alkyne but not an internal alkyne will show a CH stretch as a strong narrow band in the range of 3300 per centimeter. So these are the main vibrations: C triple bond C stretch from 2260 to 2100 per centimeter, and again C triple bond C, again CH stretch from that is 3330 to 3270 per centimeter, and C triple bond C CH bending from 700 to 610 per centimeter. And here two types of alkyne. One is terminal alkyne in upper part, and in lower part it is a internal alkyne. In this case, the triple bond is in extreme terminal side, so there is a sharp peak at 2119 around, and that is C triple bond C stretch. But in case of internal alkyne, this bond is very weak, and you can see no C triple bond C stretch visible, and all other vibrations are clearly shown. In case of aromatic hydrocarbon, the double bond CH stretch in aromatics is observed at 3100 to 3000 per centimeter. As you know, sp2 hybridized CH stretch after 3000, that is around 3100. Note that this is at slightly higher frequency than the CH stretch in alkanes, and this is a very useful tool for interpreting IR spectra. Only alkenes and aromatics show a CH stretch slightly higher than 3000 per centimeter. Compounds that do not have a C double bond C bond show CH stretching only below 3000. It means if a compound does not have any C double bond C bond, so it means CH stretch only below 3000 per centimeter. And aromatic hydrocarbons show absorption in the region 1600 to 1585 per centimeter, and 1500 to 1400 per centimeter due to carbon-carbon stretching vibration in the aromatic ring, and bands in the region that is 1250 to 1000 per centimeter are due to CH in plane bending. Although these bands are too weak to be observed in the most aromatic compounds. Beside the CH stretch above 3000 per centimeter, two other reasons of the infrared spectra of aromatic distinguish aromatics from organic compounds that do not have an aromatic ring, that is 2000 to 1665 per centimeter. This is weak band known as overtone, and 900 to 675 per centimeter, that is out of plane or up band, also observed in case of aromatic compounds. Here is the case of alcohol, and the most prominent band in alcohol is due to the OH bond, and it appears as a strong broad band overlapping the range of about 3000 to 3700 per centimeter, and the seed size and broad shape of the band dominate the IR spectrum and make it hard to miss. The exact position and shape of this band depend largely on the degree of hydrogen bonding, and the CO stretching in phenol or alcohol occur at a lower frequency range, that is 1250 to 1000 per centimeter, and the coupling of CO absorption with adjacent C single bond C stretch mode make it possible to differentiate between primary, that is around 1050 per centimeter, secondary around 1100 per centimeter, and tertiary around 1150 per centimeter, and alcohol and phenol, that is around 1220 per centimeter. And here is two spectrum. One is for alcohol and other is for phenol, and these two are, again, here is OH, which is observed at around 3000 to 3700 per centimeter, and other absorption ranges likewise. And here is the aldehyde and ketone. Carbonyl compound are those that contain the C double bond O functional group. In aldehyde, this group is at the end of the carbon chain, whereas a ketone, it is in the middle of the chain. As a result, the carbon in the C double bond O bond in aldehyde is also bonded to another carbon and a hydrogen, whereas the same carbon in a ketone is bonded to two other carbons. Aldehyde and ketone show a strong, prominent, straight-shaped band around 1710 to 1720 per centimeter, right in the middle of the spectrum. This band is due to the highly polar C double bond O bond. Because of its position, shape and size, it is hard to miss. Because aldehyde also contains a CH bond to the sp2 carbon of the CO bond, and also show a pair of medium strength band position about 2700 to 2800 per centimeter, and these bands are missing in the spectrum of ketone because the sp2 carbon of the ketone lacks the CH bond. So that's why in the case of aldehyde, this CH stretching is visible, but in case of ketone, this C double bond O attached CH stretching is absent. So and other absorptions are somewhat similar. Here is the carboxylic acid. A carboxylic acid functional group combine the feature of alcohol and ketone because it has both the OH and C double bond O bond. Therefore, carboxylic acid show a very strong and broad band covering a wide range between 3300 to 2500 per centimeter for the OH stretch, and the carbonyl stretch C double bond O of carboxylic acid appear as an intense band from 1760 to 1690 per centimeter, and the CO stretch appear in the region 1000 320 to 1210 per centimeter, and the OH band is in the region 1440 to 1395 per centimeter and 950 to 910 per centimeter. Although the 1440 to 1395 band may not be distinguishable from CH band in the same region. Here is the spectrum of carboxylic acid, and main stretching vibrations are shown here. It is customary to refer to the absorption frequency of a saturated aliphatic ketone at 1715 per centimeter as normal value, and changes in the environment of the carbonyl group can either lower or raise the absorption frequency from the normal value. These factors are inductive and resonance effect. In acid chloride, the halogen atom strengthens the CO bond through inductive effect and shift the C double bond O stretching frequency even higher than are found in esters. Second one is conjugation effects. Greater is the ability of delocalization of electron, the more is lowering in C double bond O stretching frequency. And next, ring size effects. 6-membered ring with carbonyl group, for example cyclohexanone, absorb at normal value, that is 1715 per centimeter, but decrease in ring size increases the CO stretching frequencies. And the last one is hydrogen bonding effects. Hydrogen bonding to a C double bond O group withdraw electron from oxygen and lowers the C double bond O bond character, and this results in lowering the C double bond O absorption frequency. More effective is the hydrogen bonding, higher will be the lowering in C double bond O absorption frequency. So it's clear. Now in the case of amine, the most characteristic band in amine is due to NH stress, that is around 3400 to 3250 per centimeter. In case of primary amine, two bands again observed at 3400 to 3300 and 3330 to 3250 per centimeter. Secondary amine, one band from 3350 to 3310 per centimeter. In tertiary amine, no band in this region. And NH band, primary amine only from 1650 to 1580 per centimeter. CN stretch again aromatic amines from 1335 to 1250 per centimeter, and again CN stretch aliphatic amine from 1250 to 1020 per centimeter, and NH wagging primary and secondary amine only from 910 to 665 per centimeter. And these are the region where main absorption occur, and these are the values of absorption frequencies, and these are the references where we prepare my lecture. Thank you very much.